Pluto's path was bound to cause issues from the start. Pluto's orbit intersects that of Neptune, a different planet, the mysterious and diminutive world located in the most remote parts of our solar system. Pluto has become a hot topic in astronomy. Recent updates suggest a potential collision with Neptune, raising alarms in the scientific community and among space enthusiasts. Renowned figures such as Michio Kaku and Neil deGrasse Tyson have expressed concerns regarding the potential consequences of this celestial encounter. But how did Pluto end up on a collision course with Neptune? And what might this war between the galaxies mean for Earth? Join us as we explore the details of how a massive event with Neptune might occur, and why scientists are troubled. Pluto, once celebrated as a full-fledged planet, underwent a dramatic reclassification as a dwarf planet largely because of its erratic orbit. In spite of this reduction, Pluto continues to fascinate and spark curiosity within the astronomical community. Recent warnings from prominent scientists such as Neil deGrasse Tyson and Michio Kaku have suggested that Pluto's path could cross that of Neptune, implying a potential risk of collision with serious consequences for our planet. Pluto's journey around the Sun is extraordinary due to its unique characteristics. Its orbit is exceptionally long, taking a massive 248 years to complete. Since its discovery in 1930, Pluto has not yet finished a full revolution around the Sun. What makes Pluto even more intriguing is the extreme elliptical shape of its orbit, in stark contrast to the nearly circular orbits of the major planets. Additionally, Pluto's orbit is tilted at an angle of 17 degrees relative to the ecliptic plane, resulting in a steeper incline compared to the paths of the other planets. This combination of its elongated orbit and its inclination adds complexity to its motion. A remarkable aspect of Pluto's orbit is how it repeatedly comes into contact with Neptune's orbit. Every 20 years, Pluto's path brings it closer to the Sun than Neptune's, challenging our expectations of their relative positions in the solar system. Further exploration reveals that Pluto's orbit is far from a perfect circle. Instead, it follows an elliptical or oval path, meaning its distance from the Sun varies significantly throughout its orbit. At its closest point, Pluto comes within approximately 30 astronomical units, AU, from the Sun. At its farthest, it extends over 49 AU, nearly double Neptune's distance. Moreover, Pluto's orbit is inclined at an angle to the orbits of the other planets, adding another layer of complexity to its relationship with Neptune. This inclination significantly impacts how Pluto and Neptune interact. When their orbits cross paths, their gravitational forces tug at each other, gradually modifying their courses. The relationship between Pluto and Neptune emphasizes the interconnectedness of the solar system, with each planet exerting gravitational forces that influence others' movements. Advancements in observational technology have allowed astronomers to track Pluto's movement with greater precision. This has led to a better understanding of its orbit and its potential impact on the stability of the outer solar system. Despite the possibility of a direct collision between Pluto and Neptune remaining low, it is still under scrutiny. Ongoing monitoring continues, as the potential consequences of such a collision could be significant. Despite Pluto's small size and distant location, it continues to be a subject of fascination for scientists and space enthusiasts alike. A key question that arises is, why hasn't Pluto collided with Neptune already? The answer lies in the gravitational pull of other planets. From the moment Pluto was discovered, astronomers have attempted to comprehend its path. In contrast to most planets, which maintain a consistent orbit along the ecliptic plane, Pluto's orbit stands out with its steep angle and elliptical shape. The mystery deepened when it became clear that Pluto's orbit crosses Neptune's. Despite this apparent threat, Pluto's orbit remains remarkably stable, demonstrating the sophisticated mechanics that govern space. Investigating how Pluto, Neptune, and the Sun interact presents a considerable challenge. Predicting their movements involves a deep understanding of how they influence each other's paths. To address this challenge, scientists rely on terms such as apsidal libration, latitudinal libration, and the VSOP oscillation, named after scientists von Zippel, Steves, and Kaplan to solve this cosmic puzzle. Apsidal libration, for example, is essential in maintaining the stability of planetary orbits. When Pluto crosses Neptune's path, it remains at least 90 degrees away, preventing a direct collision. Latitudinal libration ensures that when Pluto nears Neptune or other large planets, it is positioned above or below their paths, reducing the likelihood of a crash. The VSOP oscillation explains why Pluto's orbit appears unusual, yet remains stable over time. Even though space seems chaotic, underlying patterns help maintain order. These patterns are responsible for preventing Pluto from colliding with Neptune or significantly altering its orbit. The concept of orbital chaos, a description of how a celestial body's trajectory is highly sensitive to its initial conditions, is clearly demonstrated by Pluto's orbit. Even the tiniest variations in Pluto's position or velocity can have profound effects over long periods. Scientists make use of cutting-edge computer simulations to model Pluto's interactions with other bodies in space, such as Neptune, and to explore the consequences of even minor changes in its trajectory. In the late 1980s, these simulations uncovered something interesting. Despite the apparent stability of Pluto's orbit, it can still behave unpredictably. A tiny alteration in Pluto's starting point or velocity could lead to significant changes over time. However, even with these uncertainties, Pluto's orbit remains stable for billions of years, suggesting that despite its erratic appearance, it follows an underlying order. The erratic nature of planetary orbits like Pluto's makes it difficult to predict long-term changes with certainty. These models require highly precise initial conditions. Even small errors in data can produce vastly different results, making accurate predictions incredibly challenging. Understanding Pluto's orbit is essential, particularly when considering the potential for a future collision with Neptune. This knowledge contributes to a deeper comprehension of how our solar system operates. Pluto's orbit serves as an example of how seemingly chaotic paths can ultimately reach a balance, guided by the forces of gravity and motion. It is vital that we continue to observe and study these celestial mechanics to gain a better understanding of Pluto's position in the universe. Pluto's orbit is unlike that of the other planets. Its oval shape results in erratic encounters with Neptune. This irregular motion makes it difficult to predict the long-term dynamics of the system. However, gravitational forces play a crucial role in keeping Pluto and Neptune from colliding. Gravity, a force that attracts objects to one another, ensures that despite their intersecting orbits, the two bodies remain apart most of the time. These interactions reflect the delicate balance of forces at work in space. The possibility of a collision between Pluto and Neptune, while improbable, would be a monumental event with significant consequences. Such an event would drastically alter our understanding of the solar system. Though space exploration has advanced considerably, Pluto's orbit serves as a reminder of the many unknowns that still exist. Scientists continue to study Pluto's path to better understand how large planets influence its motion. This knowledge is crucial for understanding the intricate relationships between celestial bodies and how their movements can impact one another. Despite the unusual nature of Pluto's orbit, some of the world's leading scientists, like Neil deGrasse Tyson, have believed that Pluto could one day collide with Neptune. Tyson Pluto is viewed by a prominent astrophysicist as more than just a dwarf planet. Changing its status from a dwarf planet is seen as a necessary step in acknowledging the importance of continued exploration and study. He believes that Pluto's strange orbit gives it significance, as there is still much to learn about space and the forces at work within it. According to Tyson, the mysteries of space are what make studying it so captivating, and he encourages others to engage with the fascinating complexities of celestial mechanics. Tyson, along with other experts, is concerned about the potential dangers posed by Pluto's unusual path. If Pluto and Neptune were to collide, it could have catastrophic consequences for our solar system. The release of energy from such an event would be immense, and the debris scattered throughout space could have far-reaching effects. potentially even impacting other planets and moons. Neptune itself would be affected, and its orbit could be altered, further complicating the dynamics of the outer solar system. Renowned theoretical physicist Michio Kaku, who is known for his work in string theory, also provides valuable insight into space exploration. Kaku believes that studying phenomena like Pluto's orbit is essential for comprehending the larger concepts of theoretical and celestial mechanics. He suggests that the study of Pluto's interactions with Neptune can help scientists navigate future space missions more safely. Kaku also emphasizes the importance of understanding the forces of gravity in the context of space exploration, as they have the potential to shape the future of how we explore distant worlds. His work in string theory, which seeks to explain the fundamental forces of the universe, aligns with his interest in Pluto's orbit. A collision between Pluto and Neptune could offer valuable data that would contribute to our understanding of gravity and spacetime, areas central to string theory. Although such an event would have minimal direct impact on Earth, it could provide a unique opportunity to study the behavior of extreme conditions and fundamental forces. As scientists continue to delve into the vastness of space, the unpredictability of planetary interactions becomes more apparent. The study of celestial dynamics, such as the intricate relationship of gravitation between Neptune and Pluto, offers useful hints about the fundamental laws of the universe. By continuing to monitor and study these phenomena, we move closer to understanding the vast and complex nature of the cosmos. The gravitational dance between Pluto and Neptune highlights how even distant planets can influence one another. These celestial bodies exert gravitational forces that, over long periods, can shape their orbits in significant yet subtle ways, while a direct collision remains unlikely. The possibility cannot be entirely ruled out, leading to ongoing observation and interest from the astronomical community. Scientists believe that understanding these forces could one day allow them to predict, and potentially mitigate, the risks posed by such cosmic events. One intriguing aspect of planetary motion is how apparently random or chaotic interactions can lead to stable, predictable patterns. This phenomenon is particularly true in the case of Pluto, whose orbit may appear erratic, but actually follows the rules of precise gravitational forces. These forces prevent Pluto from colliding with Neptune, despite the apparent overlap in their paths. The delicate balance between the gravitational pull of other planets and Pluto's own orbit keeps the dwarf planet on a steady, though complicated, course. This complex relationship is necessary for enhancing our understanding of the larger solar system. As researchers continue to study the unique characteristics of Pluto's orbit, they also look toward other areas of space exploration. The study of systems like the TRAPPIST-1 system, which contains multiple Earth-sized planets, helps astronomers learn how gravitational forces between planets can lead to orbital resonances and, in some cases, increase the chances of a planet's path becoming unstable. Though the TRAPPIST-1 system is not currently experiencing any collisions, scientists continue to monitor the movement of planets in these crowded environments to better comprehend the dangers and potential changes over time. Astronomers are also focused on understanding the behavior of rogue planets, which wander through space without being bound to a star.